So I just wanted to thank you very much for this invitation and also for giving me the opportunity to meet some of my former colleagues I haven't seen for quite a long time. So this talk is basically on how to find a surrogate to the classical Bayesian posterior distribution. That's what the talk is about. So I want to find a substitute to it, and I will just explain why. So I'm going to start with reminding you some classical Bayesian framework. So we observe n random variables, x1, xn, and we want to estimate the distributions of these random variables. And a common assumption, of course, when you observe random variables and when you want to do a statistical inference, you need to make some assumptions. And the assumptions we're going to do is that those random variables are i.i.d. So estimating their distribution means just distribution, their common distribution actually. And this will not be enough. We also consider a statistical model which is supposed to contain the distribution of these random variables. So the model can be parametric, but it can also be non-parametric. And by doing so, in any case, it will be parametrized. I will have a parameter space, and I will have a parameter theta star that will be associated to the supposed distribution p star of my random variables. And since I'm going to have a Bayesian approach, I'm going to assume that on the parameter space, we also have what we call a prior, which is denoted by pi, which corresponds to some prior information we have on the location on the parameter theta star. And if this statistical model is true, of course there is absolutely no way to check that the statistical model is true. But if it is true, it means that everything's as if the parameter theta star were drawn at random according to the prior distribution pi, and then my data were just drawn according to the distribution p theta star. And so in the Bayesian setting, what we do is just we inverse this conditioning and say that the posterior distribution of the parameter is just the conditional distribution of theta knowing the data. We reverse the conditioning. And that's what Bayesian people do, actually. So when the model is dominated, then the posterior distribution is actually having a density with respect to the prior, which is proportional to the likelihood function. So I'm just reminding you some very basic things about here Bayesian statistics. So this is probably one of the most elementary example you see in class the first time you see a Bayesian approach. So imagine that the statistical model is here just the Gaussian model, Gaussian distribution with variance 1. So it's a translation model, and you want to estimate the parameter theta, and you take as a prior just the standard Gaussian random distribution. So it is very easy to calculate the posterior distribution in this case. It's Gaussian. It has a variance which is over the 1 over n, and it is centered at an estimator which is proportional to the maximum likelihood, xn bar, in this model. So you can prove, of course, that you can deduce from that the posterior distribution will concentrate most of its mass around on an interval which is centered at this estimator here, and the length of the interval will be proportional to 1 over square root of n, basically. So this is actually something which is not specific to this Gaussian case. This is some general fact when you consider a parametric statistical model, which is smooth and nice. So this is a consequence of the very well-known Bernstein-von Mises theorem. So if the statistical model you use is parametric, and it is regular, and the parameter space is therefore a subset of Rk, you have a nice Fisher information in the sense it is invertible, you have a nice prior, then you can show that the posterior distribution will concentrate most of its mass, actually when n becomes large, on an ellipsoid, which will be, so this is the ellipsoid here, which is centered at the maximum likelihood estimator in the model. The axis of the ellipsoid will be given by the eigenvectors of the Fisher information matrix. And the size of the ellipsoid, which corresponds to this quantity Rn, is something that, of course, depends on how much mass you want to put on this ellipsoid, which is controlled by the parameter psi, the number of observations, and the size of the parameter space, the dimension of the parameter space, k. And you recover here the square root of k over n corresponds to what Bayesian people call the contraction rate, which is also the rate you would get if you wanted to estimate the parameter theta in the frequentist paradigm. Okay, so this is a very nice result because it bridges the Bayesian approach to the frequentist approach by using maximum likelihood estimator. Okay, so nice, so far so good. So let me go back to the Gaussian setting and take back this example. But of course, everything goes well if the model is well specified, if the model is exact. But what happens if actually my data are truly i.i.d, but the distribution of this data is a mixture of a Gaussian distribution, and I just contaminate this data set, but just putting some direct mass at a point which is very far away from 0. Okay, so most of my data with a percentage, which will be 1 minus 1 over n of my data, will be truly Gaussian, but maybe a part of them will be just a direct mass at some point. So in this kind of situation, then it's easy to calculate the fact that with a probability with at least 36%, you will have this extra point among the data set. And because this point is very far away from 0, if you calculate this estimator, it will also be very far away from 0. And it means that the posterior distribution will concentrate most of its mass on a very small interval, which is very far away from 0. So it will behave very poorly, even though actually the true distribution of my data are quite close to the Gaussian, to my statistical model, because the total variation between P star and the standard Gaussian random variable in total variation is less than 1 over n. Okay, so it is a situation where my model is just slightly misspecified. Okay, and what we want to do here is just to take back the classical Bayes framework. So I have a statistical model, which is parametric or non-parametric. I have a prior on my parameter space. But I want to design a posterior distribution, which will not be the classical Bayesian posterior distribution, but something else, in order to have some property or additional properties. So what are those properties? So first of all, of course, we want to keep some of the nice features of the classical Bayes posterior distribution. In particular, I want to keep the feature that if ever my statistical model is parametric, regular, and I have a nice prior on it, I want that the posterior distribution, this new posterior distribution, also to concentrate most of its mass on this ellipsoid. Okay? This is a nice property I would like to keep. But I also would like that the concentration properties of this new posterior will remain stable if there is a small departure from the assumption I've done at the beginning. In particular, I don't want to assume that my data are truly i.i.d. Maybe they're just independent. And even if they were i.i.d, I don't want to assume that their distribution necessarily belongs to the statistical model I started from. I just want to consider that every time I have a statistical model, it's just a reasonable approximation of the truth, but not necessarily exactly the truth, just something reasonable. And just a last point, but this is just to please Vladimir here. I just want to also try to prove a non-asymptotic theory for the concentration properties of this posterior distribution, which means to have explicit constants and not to have something which is only for n tending to infinity. Okay, so this is what we want to do. Nevertheless, I need to make assumptions, something that I really assume to be true. And the only assumption I will make is this one. I will assume that the data I've observed are independent. Not necessarily i.i.d, but independent. And I will just denote by, so they may have different marginal distribution that I will denote by p1 star, pn star. Okay? And what I want to do is to analyze the performance of this new posterior distribution in this context. Okay? If I have just independent observation with might be different marginals. So let's move to the construction of the new posterior distribution. And I will also make the bridge with the classical base posterior distribution in this construction. So it starts from the fact that you have a robust test, which is something I'm going to explain here. So don't mind about the numerical constant. It's just because at the end I want to have numerical constants. So I put some numerical constants here. So I start from a test statistic here that allows me to compare two parameters in my parameter space. So this test statistics, you can prove that it has the following property, that if ever the distribution p theta prime, so the distribution in my statistical model associated to the parameter theta prime, p theta prime is closer to most of the marginal distributions of my data, then I want that this test statistics to be large. So if it is better than p theta, if p theta prime is better than p theta for modeling the marginal distribution of my data, I want this test statistic to be large. And I want the opposite. If p theta is much better for modeling the marginal distribution of my data than p theta prime, I want this test statistic to be very small. Okay, so something you can prove about this test statistic actually. And so it's something that depends on the sum of a function psi of a ratio of densities in my statistical model. So if the function psi here is defined by this formula, it's a function which is bounded by 1. It takes the value, all the values between -1 and 1, and it's very close to the logarithm in the neighborhood of 1. And in fact, if in this formula you replace psi by the logarithm, then you will end up with this test statistic, which is just the test statistic of the likelihood ratio. Okay, that's what you would do if you want to compare two distributions, knowing that your data is either distributed according to one of them. Okay, and so because of the heuristic I've just introduced, I'm going to integrate this test statistic with respect to a Gibbs measure with a lambda which is close to 1 here. And this integral, so with respect to theta prime, will mimic, in some sense, the supremum of the test statistic over theta prime. So what happens here is that so theta is fixed, and if there exists a theta prime in my parameter space such that p theta prime is much better than p theta, this integral should be large. But if no such theta prime exists, this integral should be small. So I can associate to each theta some kind of score. If the score is large, it means theta is probably not very good. But if the score is small, then, well, theta should be some kind of good parameter for modeling my data. So what I'm interested in is the theta for which this would be small. And since I want to end up with a distribution on my parameter space, I will just take a Gibbs measure that puts most of its mass around those theta for which this is small. So this is why there is a minus here. In fact, if you replace this psi by a logarithm, or something which is proportional to a logarithm, and with suitable numerical constants, or maybe not those ones, you will end up here with the classical base posterior distribution. So there's a connection between these two constructions. If you take logarithm, you will end up with the classical base posterior distribution. If you change the numerical constant, you will end up with what people in doing Bayesian statistics call fractional Bayesian posterior distribution, which is actually the likelihood function up to some power. And it was studied some years ago in order to get more robustness about the posterior. But what we do here is that not only we have numerical constant, but we change this logarithm with this function psi, which is bounded, and mimics the logarithm. Okay, and so now I need to move on to a mathematical result. So basically, I need two ingredients to present the statistical result. So what I want to prove is that this posterior distribution will concentrate most of its mass on neighborhoods that are interesting. So I need to specify the kind of neighborhood I'm going to focus on. So I will introduce a distance. So the distance I'm going to use is the Hellinger distance, which basically says that the Hellinger distance between two probabilities is up to some constant, the L2 distance between the square root of those probabilities. So this is something which is completely independent on the reference measure you use to dominate P and Q. So it's a real distance between probabilities. And I will concentrate, so I want to find neighborhoods in my parameter space. So I will denote this way. So the neighborhood PR is the neighborhood of those parameters in my parameter space for which the Hellinger distance between P and P theta is not larger than R. So it's a neighborhood in the parameter space. It's not something that is a neighborhood on the set of probabilities, but only on the parameter space. And of course, what I want to prove is that for some suitable P and for suitable R, my posterior will concentrate on this kind of neighborhoods in my parameter space. Okay, so I just move on. And the result will, as you can imagine, will also depend on the size of my statistical model. So I need to measure the size of the statistical model and the size of my parameter space. So for those of you who are doing frequentist statistics, usually you measure the size of a statistical model by using entropy, or maybe Rademacher complexity, or all those kind of notion of dimension of a statistical model. But in the Bayesian world, of course, the dimension of a statistical model will be related to the prior you put on your statistical model and on the parameter space. So this would be related to pi. And so how do you measure a dimension using just a probability on the set? So this is what I'm going to explain in a heuristic way. How do you move from a probability or a measure to a dimension? So I just take very a simple example. Imagine that the neighborhood, which I'm interested in, is just an Euclidean ball. Okay, just imagine it's an Euclidean ball in an Euclidean space, Rk. And my prior pi is not exactly a probability, but just the Lebesgue measure. How can I recover the dimension of the space K from measuring the balls? Well, if you just calculate the volume of the balls of radius 2r, and you divide it by the volume of the ball with radius r, well, what comes out is that the ratio here will be just proportional to a power of k, and you take the logarithm of that. If you take the logarithm of that, then you end up with the dimension k up to a constant log 2. Okay, so actually the dimension of the space is related to the volume of the neighborhoods. You make just the ratio of volumes and you end up with something which is a power of the dimension, and you take the log. Okay, so this is the kind of idea we're going to use. Okay, no matter if you're parametric or non-parametric, I mean, this is the way you can measure the size of a statistical model or a parametric space. So this is an idea that was introduced earlier by Lucien Birger when he was studying classical based posterior distribution. So introduced this kind of dimension function, which is taking the log of volumes of balls, of neighborhoods with radius r and 2r. But in the general case, this kind of function will depend on r and will depend on theta, on the element of your parameter space. But if you calculate, you can associate to this something which is called a dimension function. You can associate what I call an accuracy. But people in the Bayesian world will probably call it a contraction rate, which depends, of course, on the point, depending whether your prior put more mass or less mass around the point theta. And if you calculate this, you will end up with a contraction rate, which is usually, if you do things quite well, you will be some kind of optimal. So just to give an example, because that might not be clear, that if the dimension function is dominated by a quantity k, then if you solve this, you will end up with a contraction rate, which is square root of k over n, which is the rate you would expect if you were estimating a parameter of dimension k. A nice feature of that is that it's something which is only depending on the statistical model you use. It's not at all connected to the true distribution of your data. It's something you can calculate, because you choose your statistical model, you choose your prior, you can calculate this. It's just something which is known to the statistician. Okay, so now I have the two ingredients. I have the neighborhoods I'm interested in, and I have this notion of dimension. So we can establish a theorem that says that you have independent data, they have possibly different marginals, you have your favorite statistical model with a prior, and you can say that for all psi positive with a probability close to 1, the posterior distribution will concentrate most of its mass on a neighborhood, which is on the parameters theta, which are close to p star, and p star here is just the average of the marginal distribution of the data. Okay, so what you prove is that this posterior distribution, this new posterior distribution, will concentrate most of its mass around p star, which is the average of the marginal distribution. And the r star is kind of contraction rate, will depend, of course, on the level of mass you want to put on this set. So appears here, actually the compromise between two quantities. So you look at the parameter in your parameter space that approximate well this average of marginals, and plus the rate you would get if you were in a situation where your data were truly i.i.d. with a distribution p theta. So if the model is well specified, if everything is perfect, then p theta star would be an element of my statistical model. This quantity, which is an approximation term, will be 0. And it says that you will just concentrate at the usual contraction rate that people in Bayesian statistics will calculate. But if it's not the case, but if there exists an element in your statistical model which is close enough to most of the marginal of your data, then it means that you would get a concentration rate which is almost the same as if you were truly in the statistical model and if your statistical model were exact. So this is where the robustness and the stability of this new posterior distribution comes from. So it's not very difficult to deduce from this result that if you start from a statistical model which is regular and parametric and you have a nice prior on it, that you can prove that this neighborhood here will just be a subset of the ellipsoid we started from, almost, except from the fact that this ellipsoid is now centered at the true parameter theta star. And it has the same shape, and it has the same size as you would get if you were really doing classical Bayesian statistics. Okay, so just for illustration, I go back to the Gaussian example I started from. Okay, so I'm still in a situation where the model is slightly misspecified. Okay, I have contaminated my data set by a point A, which can be very far away from 0, or theta star. Now that's the true, well, most of my data are drawn according to a Gaussian distribution with centered at theta star. And the number A can be very far away from theta star. And what you get as a byproduct of what I've shown you before is that this new posterior distribution will concentrate most of its mass on the point, around the point theta star, even though the number A can be very far away, so the number has absolutely no incidence on the fact that the posterior will concentrate around theta star here. Okay, so this is all I wanted to say about the result, but I just want to mention how the ingredients of the proof, which is actually not very difficult. It just needs 2 ingredients. One being to find a good test statistics, the theta prime, allowing to compare two parameters in the parameter space. And the other ingredient is actually something that has been proven by Audibert and Catoni, which is a quite, it's a nice result. And it's difficult to explain where the intuition comes from. I mean, it comes from the head of Olivier Catoni. But basically, it's some kind of mixture between a Jensen inequality and a Fubini inequality, because you have this expectation with respect to one variable, and you integrate with respect to the other variable, and you can just swap the integration. Actually, the proof of that is not actually based on Fubini or Jensen's inequality. It's something which, the original proof of it, I mean, it's based on information theory. And with these 2 ingredients, it's not very difficult to prove the theorem I've shown you. So concluding remarks, so what we've tried to do is to provide a new type of posterior distribution to keep some of the nice properties of the classical based posterior distribution, but also to have some stability with respect to a departure from the assumptions we started from on the statistical model. I just mentioned the fact that what I've shown you here was based on neighborhoods based on the Hallinger distance, but actually you can do neighborhoods with respect to other losses. You can use L1 losses, LG losses, Bayesian losses, whatever. Maybe not all the losses you have in mind, but a lot of losses, possible losses. Just to mention, among those losses, maybe one which would be popular is the total variation loss that people could use. Why this loss would be interesting is because in some cases you can prove that using this kind of losses will give you more robustness or more stability with respect to contamination, for instance. But there's actually a price to pay. If you use total variation, you might get more robustness, but you may lose optimality. So you can have some statistical models for which, if you apply those results with total variation, you will converge at a rate which will be suboptimal. And the advantage of the Hallinger distance I've introduced before is that you guarantee that you always have the optimal concentration rates. But on the other hand, for some statistical model, you may not have as much robustness as for other procedures. So it's not something, I don't know any procedure which would have as much robustness as would give something based on total variation on the one hand, and on the other hand, always guarantee optimality. Okay, and then I just end up with some references. I don't know for the inequality given by Catoni, I don't know if it is published somewhere, I just can't find it on arXiv. Well, thank you, that's all I wanted to say. Thank you.